All right, so with this, and remember these are all ACT problems, so they are, you could very well see questions like this when you take the ACT, and part of the goal for this class is to get you guys prepared for the ACT, not just teaching you geometry concepts, but teaching you just general math fluency, and this is a question that falls into that camp. So you just kind of need to be comfortable working with numbers, and all we're doing here, I hope everyone can do the first step of this, which is just to plug this in to both of those x's right there. So the very first step is going to turn this to 8 times 1/2 minus 3 over 1/2. So hopefully everyone's comfortable with that part of it. Now, if we just look at the numerator part, this is probably something that everyone can handle. And first thing we want to recognize is 8 times 1/2. Anytime we're doing 8 times 1/2, that's the same as 8 divided by 2. All right, or if it was 1/3, it'd be 8 divided by 3, but in this case it's 1/2. So that's the same as 8 divided by 2, and we know that that is just 4. So actually I will do it this way. So that's going to be 4 minus 3 over 1/2. And of course we know 4 minus 3 is 1. So 1 over 1/2, and this is where you might have gotten to this point and you got a little bit confused on what to do here. So essentially what this is when you have a fraction, it's essentially division. So don't ever forget that. And I'm going to rewrite this real quick as 1 divided by 1/2, because that might make it look a little easier for you. And does anyone remember, this is something you would have learned in middle school, maybe even late elementary school, but probably middle school. 1 divided by a fraction. So if we divide by a fraction, what do we do to do that?
You multiply.
Multiply. So I'm going to change this to 1 times, and I'm going to go ahead and write the numbers. So we're going to multiply not by 1/2, we're going to multiply by 2 over 1. What do we call it when we flip a fraction? Does anyone remember that term? Okay, and this is one of those math terms that it's easy to forget. It's called a reciprocal. Okay, so you multiply by the reciprocal. Okay, and 2 over 1, anything over 1 is just the numerator itself. So that's the same as 1 times 2, and 1 times 2 is just 2. So the answer here was actually G, or B, when you put it on the poll. Okay, and that is how we go about doing that. So hopefully, I know you guys haven't done math in a while. You might have done a little bit of it in some of your classes last semester, but this is your first math class since last spring break. So because some of you might not have done much after spring break. So anyways, just good to get back into the swing of things, trying to remember some of these concepts. So what we're looking at today, we've got just a few things to talk about. This won't take too long. So let's just jump right into it. We are talking about constructions and geometric constructions, and there's a specific meaning behind that, and we'll get to that in just a minute. But first, we need to make sure we know a few terms. Parallel lines. So does anyone have what they think is a good definition of parallel lines? Or does someone want to just draw some parallel lines on the screen? Okay, there we go. We got a couple of drawings of parallel lines, and those both great. So very good. I'm going to bring up the definition here. Just a second, sorry. There it is. 2 lines on the same plane that never intersect. Now, this little bit right here where it says on the same plane is not something we typically need to worry about, but technically you can't just say 2 lines that never intersect. Imagine we have 3 dimensions. And so you have 3 different dimensions right there, and we're looking kind of in space. If I had a line that was going along like that through space, and then another one down below it that looked like this, technically those lines never intersect if you imagine that in 3 dimensions. But of course, we know what we're talking about. And so 2 lines on the same plane that never intersect. And people are pretty good with understanding that that term. It's the next one, perpendicular lines that can cause a problem. So again, either someone can tell me a definition, or if you think you can draw perpendicular lines on the screen, please do that. Okay, no pressure if no one wants to give it a shot. I hope a lot of you out there are at least kind of at that point where you're like, I think I know what it is. I'm not necessarily, okay. We got a couple of drawings. And actually what you just drew, Dalen, looks really good. And hopefully a lot of you were like really close. You're like, I think I know what perpendicular is, but I'm not gonna draw it. So anyways, this is good. And you can leave that drawing up there, because here's the definition: two or more lines that intersect at a right angle. So these two lines are intersecting, and the right angle, I'll just draw it on there, looks like that. How many degrees are in a right angle?
90.
90, very good. So this is just a special case where two lines intersect at a 90-degree angle. And this is one that, again, can cause a little bit of confusion, but this is going to come up very frequently throughout this entire course. So the sooner you can kind of commit perpendicular and what that means to memory, the easier it's going to be for you. All right, so I'll go ahead and clear that away. The last thing that we have as a definition is bisect. And this is one that you might never have heard before. Maybe you have. Maybe you can probably guess what it is. I don't know. But if anyone wants to take a guess on that, you can. Okay, hey, that's a good guess. That's a good guess. So the idea that I'm getting behind bisect, okay, you're like cutting it twice. And that's actually a really good guess, because it does have to do with intersecting twice. So you could think of the bi frequently means two as a prefix. So that's a really good guess. Here's what it means. It means to cut something in half. So it's not that, but I still appreciate that. And I think it's a very good guess. So if we were looking at a segment like this, if we cut it in half, we could have a line coming through just like that and cut that into two equal parts. So these little hash marks that I drew right here, those mean that the two sides are congruent and they're equal. Okay, so you hopefully have seen that notation before. And this, what I just drew overall, is what's called a perpendicular bisector. Perpendicular because it is 90 degrees. Bisector because it's cutting right through the middle. And this might be segment AB right here. So that's a perpendicular bisector. And we're going to come to that one again later. There's another kind of bisector, which if you have an angle. All right, so I'll just call this angle ABC. And if I wanted to cut this angle in half, I would need to have another ray cutting right through the middle. And what this does is, let's say that this is originally a 60-degree angle. What a bisector would do is it would cut it into two angles that are both 30 degrees. So cutting something in half, that's the idea. All right. Very good, very good. That's all that we need for definitions. Now, there are other things that I will probably define as we go through. In the past, if this is a normal school year, I'd probably give you these definitions and have you memorize them and to some degree. I'm not going to do that, but if you never remember what terms mean and you hear me say something and you don't know what it is, feel free to note that down. So don't ever get too to the point where you don't know what's going on because you don't understand the language. So let's move ahead, and we're going to talk about constructions in general. So classic constructions, and when I say classic constructions, I'm talking about going all the way back to the ancient Greek people. Anyways, those were made generally using just two different tools. I'm going to send a message real quick. Okay. And the two tools that they use, one of them, you should be familiar with both of them. One of them's a compass, not the compass for, finding north, but this kind of compass that you've probably used in years past. It looks something like this. Maybe it's got like this circle that holds it together. There's different ways that it can kind of work. Sometimes it has this little screw feature in the middle that kind of separates it out. Of course, you'd have a pencil on one side. Let's say the pencil is right here. I'll just put a dot. Let's say that's a pencil and this is like a sharp point. And you've worked with those before. What kind of shape can you create with that tool?
A circle.
A circle. And it doesn't seem that versatile because in the past you might have just worked with a compass, you drew a circle and maybe you didn't do too much more with it. So if that was the center of our circle, we could draw a circle around it. And we end up with this measurement right here. I put the R down. What does that stand for?
Radius.
Radius. Okay, good. You guys remember this. So you got radius, and no matter where you go from the center to the edge, you're going to have the same measurement. All those radii are the same, and that's going to be an important concept that we'll come back to. The other tool that the ancient Greeks had at their disposal was a straight edge. And this is exactly what you think it is. It is anything with a straight edge. So they would have had something similar to a ruler, I imagine. We have a ruler. The difference is when we have it, we don't care about all the measurements. So if we were doing this in class, we would never or almost never measure like inches or centimeters. We just use it as a straight edge, hence the name. So I can make, this one's obvious enough, I can make straight lines with a straight edge. I can make circles and straight lines. So I'll get rid of that. And even though that seems pretty limiting, so those two shapes, those two features, those are the only things we've got. We can actually construct quite a bit just using those two tools. And if you really got into this, you could learn dozens of different constructions that are possible. We're only going to look at 3 constructions overall because it gets the point across, and it helps to reinforce some concepts about these shapes. So I'm going to start with constructing an equilateral triangle. And before I just tell you how to construct an equilateral triangle, I want you guys to try and imagine how that would be possible using just a compass and a straight edge. And just to remind you, you can't use like the inches measurement. So think about that for just a minute. If you don't come up with an answer, that's okay, but just try and think through it. Okay, I mean, that's okay. If no one wants to share, that's fine. I didn't know if you had a something that you wanted to show as far as an idea you came up with, but I can run through how to do this. Okay. So keeping in mind that we're only working with straight lines and circles, I'm pretty limited, and I could just, of course, draw some straight lines and hope that this is an equilateral triangle. I guess maybe that's one thing that's important to understand. Equilateral triangles, that's a triangle where all 3 sides are congruent. That looks close, but I wouldn't be confident that it's an equilateral triangle. So I do need to use the compass. In fact, I'm going to start with the compass. And what I can recognize is if I put the stylus, the actual kind of sharp point on A, and I measured over, I'll just use this right here to represent the compass. So if I measured the compass over to point B, then I could spin this thing around and create a circle. In fact, that's what I'm going to do. So I'm going to get rid of everything and then draw that again. Oops, I don't like that circle. Okay, it doesn't look great. If we had a real compass, we could make a nice circle. Now, what if I took that same circle? Well, actually, before we talk about that, this right here is my radius because that's the distance I measured. And so no matter where I draw a line, I should get the same measurement. So knowing that, we've got one radius that we're working with. And let me now draw another circle, and I'm going to put the stylus now at B. Again, the stylus is the sharp point, and I'm going to measure over the same radius, but now I'm going to create a circle going around the other way. And now I get a circle that looks like this. Okay, this isn't looking very good right now, so I'm going to maybe try this a second time. I know I'm not working with an actual compass, so I just want it to look close enough. We're going to call that good enough. So I just drew two circles. And the thing with circle B, now we name circles by their center. So this right here is what we call circle A. And this right here is circle B. All right, so the radius for both of these is the same because I took this measurement from A to B and that was my radius. So right here, that's the same radius. That's the same radius. This is the same radius. And that's going to come into play in just 1 second. So let me get rid of this clutter a little bit. And I know that this point is an intersection, and this intersection is important. I have another one down here, but we'll just look at the top one. Because if I measure from A over to that, well, that's just another radius for circle A. So that's a radius. And it's also a radius for circle B. That's where those two circles meet. So that's another radius. So if all these radii are forming this triangle, then what I end up with is an equilateral triangle. Okay, and a lot of constructions kind of start with this basic point, and then it kind of can go from there. So I'm going to go through that process one more time. So again, I would start by drawing circle A with the radius right here. I'd want to measure that radius. And then I could draw a circle B using the same radius. And then wherever these two meet up, and this time I'll use this one at the bottom. I know these circles don't look very good, but now where I connect these should all be the same length. They're all the radius. So that's the general idea. Okay, any questions on that?
Don't they use this in art sometimes to make their lines like symmetrical and like perfect, sort of?
Oh yeah, a compass can be used for all kinds of different things. In fact, if you've ever seen, in art, definitely it can be used, especially because it's actually a lot easier to transfer distances that way. So imagine that you've got something over, I don't know, I'm drawing a rectangle. It can be anything, but the height of this is something that matters to you, and you want to kind of have the same height on the other side for symmetry purposes. I could get out a ruler and I could measure it and then draw that same thing, or I could just get a compass and I could measure from there to there with the compass and then quickly come over here and draw a little mark over here to show that same distance. So a compass can actually work really fast for measuring distances if the actual numerical distance doesn't matter. Another thing you might see it used in is anything related to orientation, navigation, stuff like that. So if you've ever watched movies where they're doing navigation by hand on an old sailing ship, you've probably seen the captain using a compass and like kind of rotating it along. So he'll just do this measurement right here. He knows how long this is on the map. That might be like 10 nautical miles. And then he can move it along and say, oh, there's another. And there's another. So that's 30 now. Now we're at 40 nautical miles and so on. So that's a lot easier than maybe trying to do it different ways. So absolutely. All right, real quick, let me know you're here. Raise your hand. So luckily this next construction is very straightforward. But before we do it, I need to explain what a perpendicular bisector is. We did already see it, but I just want to remind you, a bisector cuts something in half. In this case, we have a segment to begin with. So I want to draw a line that cuts this thing in half. It bisects it, plus it's perpendicular to the line. So a perpendicular bisector. And when we draw this, it is a line. So if I add those arrows at the end, that turns it into a line. So that's what my finished drawing should look like. Okay, Now, luckily, we have a really quick way of doing that since we already know how to construct an equilateral triangle. So I'm going to start the same way. I'm going to draw a circle here. I'm not drawing circles very well today. And I'm going to draw a circle there. So far, exactly the same thing. I could connect those together, make an equilateral triangle, but I'm not interested in that this time. And this isn't going to look very good, so I'm going to try this one last time. Still not very good, but we're going to make it work. No, I got to try one more time. Okay, that's going to be our best one yet. Still doesn't look very pretty, I know. So you probably noticed that we have these points above and below. Now, I'm not actually drawing equilateral triangles here. I'm going to pretend that I'm just measuring this distance. And I know that this distance right here and this distance right here are the same because they're both radii of the same circle. I also know that these two distances right here, I'll do this in a different color actually. Let's go with this color. That these two distances right here are also congruent. So what I've got is these 2 points. No, I wanted to change color. Sorry, this is taking a second. So these 2 points that I'm marking in blue are going to be the same distance from A as they are from B. And now if I connect these together, I know it doesn't look right according to how I did this, but if I had done these circles correctly, this would be right in the middle, cut it in half, and it's perpendicular. So it's one of the properties of a perpendicular bisector that these 2 points are going to be the same distance. So these 2 points in blue, I'll call them C and D, are going to be the same distance from A as they are from B. And that puts it right in the middle. And when I connect them, it creates a perfectly perpendicular line. So it's just basically as easy as the equilateral triangle and a very simple construction. I'm going to just run through it one more time, and then we will look at the homework, and we're basically done at that point. So I've got circle A, I've got circle B. Is this my best one yet? The circle B doesn't look very good, but connect these 2 points together. That's C and D. And there we go. This line has cut this in half and it's perpendicular. It's that easy. So I will go ahead and move on to the homework. And I just need to show you how to do this in Delta Math. So you hopefully have the idea. If you still have any questions on the process, please make sure you stick around afterward. But if you feel good with it, let me just show you how you're going to do this in Delta Math. Okay, so we are going to construct an equilateral triangle to begin with. Okay, so what they give you are a few tools. You can create compasses, segments, rays, and lines. So just to show you real quick, a segment, of course, we just create a segment. Okay, well, never mind. I'm going to do it like that. Oh. Okay, they're not going to let me do anything right now. I was trying to, but you can see what a ray does. It creates an end point on one end, another just stretches toward infinity. A line would have 2 ends that go on toward infinity. But we need to start with a compass. So you'll notice when I hover over these points that I can select them. So as I do this, I started at K, and I'm just moving along this line, and notice that this dashed line circle gets bigger and bigger. I want this to measure all the way over to J. Now this is not creating the circle yet. Notice that it creates this pencil. So now I can just quickly go all the way around. You don't actually have to follow the blue area. You just kind of roughly follow the circle. And now I've created this circle. Now, the easiest thing to do at this point, since K is the middle of my circle, if I grab this, I can move this around. And you can see now that it's almost like I've picked up the compass and I can move it anywhere I want to on the page. So I want to move this over where now J is the middle. And notice that it goes right through K again, and I can draw another circle. And I'm done with the compass. I've just drawn those 2 circles. And notice that it gives me these 2 points right here, this intersection at the bottom, that intersection at the top. So to finish this, I need to connect one of these together. In fact, actually, just to show you that the computer doesn't care, I'm going to draw it at the bottom. So I'm going to connect that right there and that right there. And this is our equilateral triangle. I just come down here when I'm done, submit the answer, and it gave me a green check mark. All right, if I made a mistake, they do have a step-by-step instruction. So you can see right here, set your compass and then draw an arc. Now they're not drawing a full circle. They're only drawing enough to get an intersection, but they do the same thing here. They just create an X where the intersection would be, and then they combine it. So it runs through the process if you forget. But let me do that one more time. Okay, and I'm going to do it a little faster, but I'm going to show you what would happen if you made a mistake. So let's say you didn't go quite far enough. You only went that far. You drew your circle. So notice I didn't quite draw my circle all the way over to C, but then I moved this compass over, and this time I did go the full distance. So now I've got these intersection points. So now I can connect these together, boom and boom. Now we can see that's not an equilateral triangle, but if I made that kind of mistake, it would give me this red X, and it would give me the option to see how it's done. So I could just try and fix my mistake. So anyways, if I, well, whatever. So if I came back, I could fix it all. And I'll just fix it one time real quick. I know a lot of you don't need to see it, but I'm just showing it for, I'll just draw this much of the arc. And then I'll move it over. I'll draw that much of it. And then I can just connect it all together. And there we go. In fact, I'll just call that good. I'm not going to check the answer. We know it's right. So you need to construct like 3 of those for homework. And then I will show you for the perpendicular bisector. Same thing, they'll give you a segment to start off with, and we know it's the same construction more or less. So I'll just draw that much of it, and I'll move it over. Actually, that's not going to work very well, so you can turn the compass off and on if you need to. I didn't need to do that, but anyways, I'm making mistakes. There we go. Now I can connect that together, and I get my 2 intersection points. And remember I said that a perpendicular bisector is a line. So if I try and draw this, if I try and draw this as a segment, it's not going to let me. I'm going to try and submit my answer, and it's going to say, oh, it needs to be a line. Okay, so I will go back. I will undo that. I'll draw this as a line instead. There we go. Submit the answer. We're good. Okay, that's all there is to it. You are good to go. If you have any questions, feel free to stick around. But if you feel like you've got it down, have a wonderful day, and I will see you tomorrow.